Welcome to the AI Research Roundup. I'm Alex. Today, we are looking at a paper from the Hugging Face trending list, published on September 5th, 2025, about 4 days ago. The standout result is that training on their fully synthetic dataset delivers strong real image performance with an MAP50 of 0.87 for rust detection. The paper is titled SynGen-Vision, Synthetic Data Generation for Training Industrial Vision Models. And as we will see later, the implications for model training are quite significant. In short, the work builds an end-to-end pipeline that blends text-to-image diffusion, style transfer, and 3D rendering to produce photorealistic, auto-labeled wear-and-tear datasets. On X, one post highlights synthetic data for industrial vision, noting a pipeline with texture generation, style transfer, 3D reconstruction, and auto-annotation matching the rust detection theme. Engagement looks moderate with around 140 likes. The opening overview just set the stakes for synthetic training gains. Figure 1 presents the full pipeline, which starts with general AI generating rust textures and labels from prompts. The 3D rendering block in Blender then places textured models into varied scenes, so images and annotations reflect realistic views. The final object detection module trains on these outputs to learn rust detection, localization, and rusting levels, producing a deployable model. Alright. The previous figure outlined the overall pipeline blocks. Figure 2 shows the step-by-step execution, which starts with the 3D model and prompts, then moves through UV map extraction, texture generation, style transfer, and 3D reconstruction. The right side displays rendering and auto-annotation, followed by training plots and final detections on real images. The sequence matters because each stage preserves surface details while adding realistic rust, so the detector learns from clean, labeled views. Trigger text. Figure 2 shows the bounding box, 0.03, 0.07, 0.97, 0.86. So the previous figure detailed the stage pipeline. Figure 3 compares visual outcomes across 3 variants, which helps explain the performance gains. The left column shows the clean input 3D models. The middle column shows general AI textures that add rust but wash out fine markings. The right column shows general AI with style transfer, which preserves surface details like bands and panel lines, while keeping realistic rust spread, so training examples stay faithful to geometry and semantics. Alright, the previous figure compared visual quality across texture variants. Figure 5 shows one rendered training image with an orange box labeled complete rust, alongside the auto-generated annotation file that stores class and bounding box coordinates. The left panel illustrates how the rusted tank appears in a realistic scene, which matters because detectors learn from context. The right panel lists file name, image size, class name, and the Xmin to Ymax coordinates used for training. So the previous figure illustrated auto-annotation. Figure 4 highlights failure cases in texture generation, which matter because noisy textures leak into training if not filtered. The panels show 4 issues: random text appearing on surfaces, watermarks stamped across textures, an incorrect degree of rust that misrepresents severity, and random objects embedded in the texture. These examples motivate the noise removal step, so rendered scenes stay realistic and labels remain trustworthy. While the previous figure highlighted failure cases and the need for filtering. Figure 6 shows sample detections on real test photos, with orange boxes and class labels for complete rust, rust streaks, and default. The top row mixes partial and streaked corrosion, while the bottom row includes heavily corroded tanks and a clean beige tank marked default, which demonstrates class separation. The confidence scores sit high, which signals the synthetic training transferred well to real imagery. Well, the previous figure showcased real image detections with strong confidence. Table 1 presents the quantitative analysis, which compares 3 training variants across classes and aggregates. The metrics climb steadily from general AI alone to general AI with style transfer, and finally, to general AI with style transfer and noise removal, which gives the best results. The all column reports MAP50 rising from about 0.279 to 0.451, and then to 0.872, showing the filtering step mattered because it boosted both precision and recall across classes. Okay, 2 takeaways stand out. A fully synthetic, auto-labeled pipeline can train a robust rust detector that reaches roughly 0.87 meters AP50 on real photos, and careful style transfer plus noise filtering are crucial for realism and transfer. The broader implication is cheaper, faster dataset creation for industrial inspection. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.